Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Wassalatu wassalamu ala rasulillah amma ba'du. Right. In this morning, we can see again to continue our study. And before we start our study, let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yasha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul hazna idza syi'ta sahla. Ya muqallibal qulub tsabbit qulubana ala dinik. Amin. Alright. So in the past meeting, we already implement problem E, right? Okay, and we also already discussed the solution for problem F, right? If you remember the solution for problem F, so in this problem, given an array, and we want to ask some queries. The queries is on a subarray of it. And its subarray, we want to know what is the core or its index in that subarray. Its index is the maximum age. So the number of values or the number of index, or there are at least 8 indexes such that the value is greater than or equal to 8. Okay. Then the idea is using binary search. So every time we check the mid, we can count the number of values that greater than or equal to mid. If the number of such index is at least mid, so it means it is valid. All right. And since the number of queries is so many, so we need to solve them using parallel binary search, right? Okay, so let me show you the implementation, starting from imputing the array and then imputing the queries. Okay. After imputing the queries, as usual, we want to do parallel binary search, starting from 1 until n. I think 1 is always valid. Yes, 1 is always valid, so we can try to check start from 2 instead of 1. Alright, what else? Okay, then we want to create a data structure. Which data structure we use? Can you predict the data structure we will use? Yes, bandwidth 3 is enough since we want to activate one by one, not arrange. So just use bandwidth 3. Alright. So these are the variables. And we need bandwidth 3. Okay. Right. So at first, let's reset the bandwidth 3 and then just do this one by one. So at first, we want to know which index is has value of m or value of I, like that. Either just sort them using pair or store them in a vector. So every time we input A, we know that I has value A. So when we add them one by one, you just need to update the bandwidth tree in that index. Okay, after that, just check whether the number of index is enough or not. Just querying them. If it is greater than or equal to I, okay. Maybe we can set R into yi minus xi plus 1. Why? Because cannot more than that. But okay, if we set it as n, it is still correct. Wait, but sometimes n is equal to 1. Let's make it like this. If still less than or equal to r, okay, just push back. If not, then just C plus plus. Okay, what else? If greater than or equal to I, then the answer is I, at least for now. Then try to find the bigger answer. If not valid, then find the smaller answer. Alright. And as usual, we find another meat. Okay. Yes. I think this is enough. In 3, 2, 1, 2, 2. Alright. Let's try to submit this. Wait, can we use for auto in C++ 11? Okay, accepted. Okay, alhamdulillah. Okay, is there any question about this solution? Can we use parallel binary search? So this is the typical implementation for parallel binary search. Okay. For parallel minors, I think the solution is not parallel binary search. Then we can go to problem 8. Okay. So for this problem, given n times n, a grid with size n times n, and we want to answer q queries. Each query is given a subgrid from R1 C1 until R2 C2, and we want to find the k minimum number in the subgrid, and all of the value must be different since it is a permutation. All right. Okay. Then before we think about the solution, we should know about the format. In this problem, the value of n is so big. Actually, not too big, but it is big enough for the input. How do you think if we input 5,000 times 5,000? Of course, it is so big. So it is impossible to input this number. That's why here the input is not directly inputting the grid, but the input is given in these variables n q seed minimum r, maximum r, minimum c, maximum C. What does it mean? From the seed, we can generate the grid. Okay. Generating the grid is using this procedure. So we just need input like this and generate grid using this algorithm. Okay. Just shuffling them. And okay. Never mind about the shuffling algorithm, but okay, we know that we will generate a random grid here. Okay. And also we generate the query here. The query is randomized between them. All right. Okay. Is there any question about the input format here? Okay. I think it is clear. So what else? Okay. So after that, how to solve it? How to find the k minimum value in a subgrid? All right. Maybe there are some solutions. One of them using the parallel binary search. So we can try to do parallel binary search like this. Wait. We can create a two-dimensional data structure and then we activate one by one and then just check when we try for the mid. We want to check whether the number of activated values is at least k or not. All right. Okay. Yes, just like that. Okay. Then do you know how to create the two-dimensional data structure? Here the time limit is 8 seconds. And the worst case for n square is around to around 25 million. Okay, then which data structure we will use? So it is okay, I think, if we use n square log n. What if n square log square n? I don't think so. The log is around 20, right? Not 20, sorry, 12. So it is become like this. If the log is 24, then it is 6e8. But if log square, I think it is the limit exceeded. Then how to do that? Okay. Is there any idea how to find the gate minimum? We can solve them offline, right? If the time limit is not too strict or the constraint of n is not too big, but wait, the number of queries is only 5,000. If it is only 5,000, then it's okay if complexity is q and log n. Yes, maybe we can use parallel binary search, and we can create Wait. Yes, we can create n Fenwick trees, for example. So in its updates, it is just log n. So the total number of updates is n square log n. And the number of queries q times log n, and each query we need n log n. Wait, here we need log square. Then how to make it faster? Do you have any idea? All right. So maybe okay, if we want to create separated data structure for each lines, then the query result be when the update is can be wait, the update also solve the when. This is if separated data structure. But if the data structure is combined, okay, if combined, then the update is also when, and the query can be on. Can we just use a bit set? Or what if we forget about parallel binary search? Let's find the other strategy. What if we have a range 3? I think the complexity is also big. All right, let's make this as our homework. And for this time, let's continue to the next problem. Okay. For this problem, it is also about graph again. So there are n nodes here. And then the query is given A and B, in which day A and B connected. So initially the cities are not connected, and then they connect them one by one until at some point A and B are connected. So in which day that node are connected. All right, just like the previous problems, right? But how to connect them? They will connect in M days, from the first day, second day, third day, fourth day until mth day. Okay. And what is the pair that connected in the first day? The pair that connected in the first day is all nodes. Sorry, all pair of nodes that the greatest common divisor between them is equal to m. If the greatest common divisor is equal to m, then connect them. So in one day, it is not only one nodes, maybe greater than one nodes. For example, m with 2m, we will connect it. M with 3m, m with 4m, we will connect them, right? Of course, we connect all multiply of m, right? Okay. And in the second day, we will connect all pair that the greatest common divisor is m minus 1. Okay, again, we will connect all multiply of m minus 1, right? Okay. Actually, we connect this as well, but it is redundant. So we will connect any multiply of this. And then we connect the multiply of m minus 2. We connect the multiply of m minus 3 and so on. And in the before last day, we will connect all multiply of 2. And in the last day, we connect multiply of 1. So is the graph is connected after the last connection? Warranted to be connected or not? How do you think? Is the graph connected based on this type of connection? We will connect all pair of nodes that the greatest common divisor is equal to m. After that, connect all pair that the greatest common divisor is m minus 1 and so on. Okay. Then is the graph connected? How do you think? Connected or not? M is always less than or equal to n. Okay, if m is equal to n, then it is complete graph, right? Since all the greatest common divisor always less than or equal to n and less than or equal to m as well. So it is a complete graph. But if m is less than n, it is not always complete graph. But is it always connected? Connected or not? Okay, let's try to predict yes or no. Connected or not. The hint is in the last day. We will connect all multiply of 1. 1 connect with 2, 1 connect with 3, 1 connect with 4, and so on. So is disconnected? Yes, of course it is guaranteed to be connected, right? It's guaranteed to be connected because in the last day we will connect everything. Alright, if an m is equal to 1, then they also connected. So how many number of important connection? So at first, since we are not connecting the complete graph, right? We only connect the multiply of m, the multiply of m minus 1, the multiply of m minus 2, and so on. So what is the complexity of it? So if you want to connect them one by one, just like this, right? So we will connect I with j like this. Can you predict what is the complexity of this code? What is the complexity of this? If you ever know about that. Okay. You know, the complexity of this, the inner loop is equal to n divided by I. So if we want to try for every I, the complexity is like this. Okay, all right. Even if this is unbounded, it is n log n, right? Or actually n ln n. And of course, if it is bounded, so less than this, but still not far from this. In the worst case, when m is equal to n, then it is also almost equal to this. So this is the complexity for this double for loop, this nested for loop. All right. Then it means if we want to do parallel binary search, if we use this, then the complexity become n log square n. I think it is still okay since n is only this. But if we want to make it faster, there is a solution. So instead of n log square n, we can make it faster. It's just n log n. How to do that? Just create a list of edge that we should connect. So initially, we want to do this. So we want to check whether I and j is in the same connected component or not. If they are same, okay, no need to connect them. If not same, so okay, just join them and then just connect them. So in the m plus 1 minus ith day, we need to connect between I and j. All right. Is it understood? So do you know how many number of pushback in the worst case? Actually, it is fixed. So the worst case is equal to the best case as well. In order to connect a graph into one connected component, we need to use n minus 1 edges, right? Because using one edge, we can connect to connected component become 1. So when initially there are n connected component and we want to make as one connected component, the number of connected components is reduced by n minus 1. So we need n minus 1 edges. All right. So if you want to implement the solution, we can just do this. First, just create an MQ and then just create a disjoint set, right? Just create a disjoint set. And then just connect them using like this. And then for its theory, we want to parallel binary search here. All right. Of course, until mth day, they are connected. So just make it m minus 1. MO is connected. So if M is equal to 1, it means just output 1, 1, 1, 1, 1. Okay, yes. This all of them will be already known. Okay. Then when we want to do parallel binary search, at first just reset the disjoint set union and then just iterate j by j. And then we will join them. We will connect the edges, the important edges one by one. And then we will join expect first, expect second. Okay. We'll join them and then when we check the query, just find the component. If the components are same, so it means in that day it is already connected. And we want to make it as early as possible. Right, I think this is enough. Let's try to create the functions. Right, okay, I think this is enough. Let's try to invite them. Yes, this is correct. All right, all of the samples already correct. So Let's try to submit. I think we should submit in the source. Okay. Yes. Alhamdulillah. Yes. But accepted. All right. So let's label the problem. For problem A, we just need disjoint set union 5. For this one, disjoint set union with size. For meteors, we need Fenwick trees as well. For minerals, we need Golden ratio. For this, we need disjoint set union with size. Size is weighted. For this, we need Fenwick trees as well. The query is range, and in this problem, the query is only points. This is not about clarifying research. And for this, we need disjoint set union only. And also we need to pre-compute the edge. All right. Until problem I, is there any question until problem H, I mean? So let's continue to problem I. Again, this is about graph. So there are n nodes and m edges. How do you think the edges is one directional or two directional? All right, since it is undirected, it means two directional, right? So The edge has a weight, or let's say it is a crowd value. So there is a crowd value for its edge, and when we move in some path, for example, we move from this node, go to this node, go to this node, and so on. The final crowd values is the maximum between all of the nodes. All right. For example, the crowd values here is 2 and here is 5. This is 3. So it means the final crowd values for this path is 5, the maximum one. All right. And for its node, the node is also weighted. The weight is equal to the type of buildings. So there are some types of buildings, and each city has a type of building TI like this. All right. And what is the query? The query is we want to go from X to Y, but we should visit at least K different buildings. And the path may contain a cycle, so it is allowed to go from some points and go back like that. Okay, it is okay. For example, we want to visit like this. This okay if we want to travel from this node to this node and then go back to Y, it is okay. It may contain a cycle. All right. And we want to minimize the crowd value. Okay. So can you predict how to solve it? I think it is quite similar with problem B. So the score is based on the largest index. For problem I, it is counted as the largest crowd value or largest weight. All right. So when we try to solve it by binary search, we can check for its mid. Right. If we want to make the answer not more than mid, it means we are not allowed to pass through the edge that is greater than mid. All right. Only use the we use some edges that is less than or equal to mid. And then since the path may contain a cycle, so it means just check the connected component, right? From X can go to every node in the connected components. Always can go there and then go back to X. And also X and Y should be in the same connected component as well. Then what else? Then the last thing we need to solve is there is another condition we have to fulfill. In that path, in the path between x and y, should exist at least k different types of buildings. Alright, it means in each connected component we should compute the number of different buildings, right? Okay. Do you know how to count the number of different buildings? Okay, let's try to think about that. But sorry, please let me go to the toilet for some minutes. Okay, let's continue. Do you get any idea how to count the number of different buildings? Building. Okay. Do you know about the SEC algorithm or small to large? Small to large algorithm. Okay. So Basically, so let's think about this, Chris, this problem. What if we do a nice solution like this? For each connected component, we create a set of types of buildings. So when we want to connect to disjoint set union, we just combine the set. Just insert every items here to the other set. All right. So how do you think? What is the complexity for any case? What is the complexity for the worst case? Of course, the worst case is when all of the types are different and the connection is like this. We want to connect this, so we will move one here, and then we want to connect this, so we need to move two here, right? Since there are the size of the set is two. And then we will move this three, right? And then we connect this, we need to move four. So how many number of moves? It is around n square, right? N square number of moves. And also since we use set, so the complexity become n square log. So it is so slow since we use a naive solution. All right. And do you know how to optimize this? How to optimize this naive solution? You don't want to use brute force one, right? So